this problem, we're going to look at correlation. Now, correlation is the square root of r squared. Fortunately for us, we have a graph right here that shows us the relationship between x and y. When we take r and square it, we'll always get a positive number. But when we take r squared and take the square root, sometimes it's negative. And we won't be able to tell that unless we look at the scatter plot. So let's go ahead and square root r squared. Going right here, we take 0.733 and square root it. Bringing this back over, I like to copy in all the numbers and then delete down until we get to the right point. Now remember, r squared is percent of variation in y explained by x. So 86% of the variation in interest rate is explained by the variation in years since 1950. Next, we're going to explain the slope and intercept. And let's do it by how we do it in the class. So with the intercept would be when the year is 1950, which is 0 down here. When the year is 1950, we would expect the interest rate to be 0.30. We're doing just the 2 decimal places. Now, with the slope, for each additional year past 1950, we would expect an increase in interest rate by 0.26%. And you can round or not round when you say these yourselves, but down here we need to make sure we round properly, because we are going to expect an increase in interest rate of, and this is the slope right here, 0.26, and make sure, I didn't say it in my speech about it just a moment ago, but make sure to round to 2 decimal places when you do this right here. When you check our answer, and we did get it correct. Always make sure you can interpret the slope and intercept for any equation you get. And now since we have the equation, we need to go ahead and use it. Remember, in your equation, it is y hat equals b naught plus b1x. b naught is the intercept, and b1x is the slope. So with this in mind right here, let's plug in b1x by plugging in the x. Well, the year 2000 is too big to type in because we're using years since 1950. That'll be 50 years. So our x is 50 years. And then we need to times it by the slope. And then add on the intercept. And that gives us about 13 because we only need to round to 1 decimal place. And now one good thing you can do is if you were to go out to about where 50 would be at and follow this up till where it would hit the line, if you notice, I'm about at 13 over there on the left scale. So yeah, that makes sense to me. About 13% this line would predict. Would you expect your prediction to be accurate? Well, no matter how good the r squared, this is an example of extrapolation. We are extrapolating 20 years beyond the scope of the model, and that's a pretty big extrapolation. It's pretty all right to go out maybe 1 year, 2 years, 3. You're still extrapolating beyond the model, but you're not doing it really far out and making dangerously far out predictions. I always think of extrapolation to a degree, but anything outside of the x space, anything, as you see, I'm moving up and down on this 30 right here, anything outside of this 30 years is extrapolation. So if someone said is predicting at would it be 1981 extrapolation? Yes. And is it really dangerous to predict at 1981? Probably not. But one thing that does scare me about this plot is the residuals. And I hope everyone's still listening. I hope you're not like, hey, why is he not talking about the next problem? But we can think about how the residuals look by taking this line right here and making it flat. If you notice, it would be right here in 1978, or this would be 1979, and this would be 1980. 1979 has a negative residual, and a rather large one, the largest. 1980 has a positive residual, and the largest. The residual plot is showing, does the plot thicken? And it does. That's not a good thing. It means we are less accurate out here. So just imagine if this fanning out gets even bigger. That means we are not having an accurate line anymore. Where a line predicted really well right here it doesn't predict so well at the end of it, which is where we want to make our predictions. That's not good right there. Always think about the residual plot anytime you have a regression plot. If you want review on that, go back to chapter 8 homework and check it out. Okay, so let's look at this problem right here. So with this in mind, we need to describe what would happen if humans were removed. So humans are right here. And just think about it. Cover them up with your mouse. That looks better. Those blue points look like they follow a line that goes up sharper, and the blue points are more tightly clustered. So it would definitely be stronger. And if you look at it, what's going to happen right here, it's not because there's fewer points. It's because this point right here would actually pull out our ellipse. A lot of times I talk about drawing an ellipse around all your points, and if that ellipse is tighter, the correlation is more like a 1. Now also the slope is going to increase because we can see because the line would go through here rather than here. Slope does not mean higher correlation. Correlation is generally how tightly clustered the points are, which is related to r squared. Going on to the next, is there reasonable justification to remove humans? Well, there's a whole bunch of animals here, so yeah, we can go ahead and remove them and just leave it to what we consider animals, which everyone says, well, humans are an animal, but let's go ahead and just put it to animals other than humans. Here's our scatter plot analyzed for the 17 non-human species. Comment on the strength of the association. This is a definitely strong correlation. It's not perfect. No way is that perfect. No way does every point fall on that line. We're looking at, I would say, even strong. That's a really strong correlation. Interpret the slope. Now, if you look over here, what we have going on is we have the slope and the intercept. And they give it to you in kind of a weird format. But you can test this out if you want. The constant is going to be the intercept, and the life expectancy is going to be the slope. And how do I know this? Well, let's plug in 40 right here real quick. So this is our B1 and this is our B0. So by plugging in 40 right here and timesing it by 13.10, oops, messed that up. 40 times 13.10, and then I add on 86.845. Now, why did I do this? Going right here to 40 and growing up to 610, I'm about right there. And if you look, that's where the line would be going through. I even have a point right there. Now, that point doesn't justify it. It's that if you were to think of a line going through this data, it would probably hit right about there. And that makes sense. So interpret the slope. For every year increase in the life expectancy, the gestation period will increase by about, and it wants it to 2 decimal places, 13.11 rounding to 2 decimal places. A certain mammal has a life expectancy of 29 years, excuse me. So estimate the expected gestation period. So we're going to go ahead and plug that in for x. 29 times 13.1080. We are just plugging 29 in as our x using B0 and B1 right there. 86.845, and we have 466.977. It says do not round to the final answer, then round to 1 decimal place. So that's actually going to round to 467. Good luck on this. Remember, always be able to interpret your values. Very important for this. Interpretation is key because we don't want to just throw out some values. Good luck.